Hey physics class, so today I'm just going to be going over the last couple of problems that I've given to you. It's going to take long enough that it's going to be a whole day's work anyway, so I'm not going to add on to any of that. So the first thing that I want to do is to give you the solution to the hot air balloon problem. So let me go ahead and get a drawing for perspective. I really hope this is the last time I have to draw a hot air balloon. I never thought I would draw so many hot air balloons, but you know, life throws you curveballs, and you just got to learn to deal. Float along. So the balloon that I gave you in the problem had these specifications. So the mass of the material in the balloon itself, you know, the basket and the fabric and all that, was 500 kilograms. The volume of the material, remember the deflated volume just of the basket and the fabric in the balloon itself, that had a volume of 10 cubic meters. Now, I want to make sure that I don't mix these up with the mass and the volume of the air. So I'm going to stick a little b here as a subscript. So that's the mass of the balloon. This will be the volume of the balloon. Later on, I'll refer to it of the air. So that'll be a subscript of a. Anyway, so we've got a mass of 500 kilograms, a volume of 10 cubic meters. Now, the volume of the air inside, that was much larger. The volume of the air was going to be 2,000 cubic meters. Can you read that? That's yeah, you can read that. All right, so that's 2,000 cubic meters. Okay, so that right there is just the data on the balloon. And if you remember, the point of the problem was we need to heat up the air so that it expands, some air molecules leave, and the density goes down to match the density of the air. So if you will recall, the density of air is equal to 1.225 kilograms per cubic meter. The idea is we need to get the density of this balloon to equal that. In other words, this quantity, 1.225, must be equal to the total mass of the balloon plus the total mass of the air contained within the inflated balloon over the volume of the balloon itself plus the volume of the air within the balloon. Density is always mass divided by volume. Since we're talking about the density of the combined balloon and air it contains, that's why I've got the sum of the masses in the numerator and the sum of the volumes in the denominator. So let's just fill in the values that we know, see what we don't know, and we'll just have to solve for them. So the mass of the balloon we know, 500 kilograms. The mass of the air inside, though, that's actually what we don't know. So we got the mass of the balloon, it's 500. Mass of the air, that's unknown. What about the volume of the balloon? Well, that's 10. And the volume of the air, that's 2,000. Please remember, the whole point of choosing a particular thing is so that it will behave, its pressure and its volume are going to change based on the physical properties of this thing. I chose a balloon so the volume would remain constant and the pressure would remain constant, and only the temperature and the amount of air inside can vary. So we've got the density of an inflated balloon. We know that it must equal this density, but before I throw that in there, let me simplify this real quick. Since I've gotten rid of MB, I'm gonna I'm gonna keep the MA because I don't want that to get lost. So this simplifies to 500 plus the mass of the air inside over 2,000 plus 10 Okay, so this is an expression for the density of the inflated balloon, and we just need to get its density to equal that amount. So we're trying to solve for the mass of the air inside. So the first most obvious thing that we need to do is we need to multiply both sides by 2010. If we do that, we're going to end up with 500 plus ma equals 2,462.25. Okay, we're almost there. To get this by itself, we need to subtract 500 from both sides. And so that means in order for this balloon to float, to be weightless, it's going to need to have a maximum mass of 1,962.25 kilograms of air on the inside. Okay, so just so we are clear, in order for this balloon to be as light as the air, there can only be 1,962.25 kilograms of air in this 2,000 cubic meters. All right? Well, in order to make that happen, we're going to need to take into account the density of air. If you look back on the previous video, we did end up finding the molar density of air. So for this case, we're going to be taking the density of air to be 0.0274 kilograms per mole. That was the number that we used in the last video. So if this is our density, and we know that the mass of air we're going to have is 1,962.25 kilograms, well then, in order to figure out how many moles of air we can fit in this balloon, we just need to divide this mass by that density. So let me write this out so you can see the units cancel. 1962.25 kilograms over 0.0274 kilograms per mole. You got your kilograms canceling. You've got 1 over moles. That's going to come up in the numerator. And so 1962.25 divided by 0.0274 is equal to an enormous number, 71,614.96 moles. Now, that number might seem huge, but if you remember from the last problem, we had in the 30,000s and in the 40,000s. So it's an awful lot of moles of air. That's not unreasonable. All right. So the question is, what temperature will have 71,614.96 moles of air have a volume of 2,000 cubic meters at 1 atmosphere of pressure? This is the situation that is described by our problem. Remember, I've got a balloon with a volume of air of 2,000 cubic meters. When the balloon has the same density as the air, that means that there's 1,962.25 kilograms of air in there, which turns out to be only 71,614.96 moles. So I've just got to set up the ideal gas law for these values and solve it. PV equals nRT. So a word about this. The volume is in liters. this volume is in cubic meters. There are 1,000 liters in 1 cubic meter. And that means that 2,000 cubic meters is actually 2 million liters. So that's the number I'm going to have to use. Okay, so let's fill this in. We know what the pressure is. The pressure is 1 atmosphere. The volume is going to be 2 million liters. I'm going to put that like this so it doesn't run off the frame. So this is PV equals, oh, I might run off the frame as it is. Let me see if I can stay in it. So 71,614.96 moles. N. R is the same number as it was in the previous problems, and that is 0.08206. That's units liter atmospheres per mole Kelvin. All right, I just barely have enough room for the temperature. But the temperature is what we don't know anyway, so hooray, I'm safe. That temperature is going to be in kelvins. Okay, so solving for this temperature is just going to be a big fat calculator bomb. It's going to be 1 atmosphere times 2 million liters over 71,614.96 moles times, sorry, that should be times, it looks like a minus, times, there we go, 0.08206. Okay, calculator does this, you end up getting an answer of 340.3. 340.3 kelvins. Subtract 273, you get 67.3 degrees Celsius, which is a nice and toasty 153 degrees Fahrenheit. Okay, there was one more problem. This is the one that I gave you yesterday. It had to do with canning. Right, so you've got yourself a jar. I'm going to draw a very basic jar, sorry. I spent all my artistic... that is a sorry looking jar. All right, so we've got a jar. The air on the inside has a temperature of 373 kelvins. That's just boiling. So basically you've got a empty jar that just came out of boiling water. So the air inside is at the same temperature as boiling water. Just say it's steam or whatever. And the volume of this jar is 500 milliliters or 0.500 liters. So we put a lid on it. The art just makes no sense. We just accept this. And then it cools down. I can't believe I have to copy this awful drawing now. It looks like mayonnaise. I have no idea. Anyway, enough art criticizing. After this cools down to room temperature, it's now 293 kelvins, still 0.500 liters. The question is, if this started out with a pressure at 1 atmosphere, what's the pressure now? So if we were to put this in the context of the ideal gas law, we've got a before, which is 1 atmosphere. The volume is 0.5 liters. Now, I'm actually not going to bother calculating the number of moles in there, and you'll see why I don't need to later. So the number of moles in there is just the number, yeah, that's totally an n. The number of moles is just the number of moles. The ideal gas constant is what it is, and the temperature before is 373. So here's one of the reasons why I don't actually need to calculate the number of moles in there. So this is before. This is going to be a container whose volume can't change, and also the number of moles inside can't change. So I've got a PV equals nRT for before, but now I've got to have a PV equals nRT for afterwards. What are all the things that are the same? The volume stays the same. It's a jar. It's not going to flex. So the volume is still 0.5 liters. None of the gases escaped. So N is still the same. This is a constant. It's still the same. There's only two things that have changed. And they are directly proportional because they're on opposite sides of this equation. This temperature has changed to 293, which means that this pressure must also have changed proportionally. So think about this like if you were doing algebra, whatever you do to the right side, you must also do to the left side. In order to get from 373 to 293, what you can do is multiply by the fraction 293 over 373. These two lines are algebraically equivalent. And because the temperature and the pressure are the only things that are changing, and they are directly proportional, you just multiply both sides by 293 over 373, and that's what you get. So this is clearly a fraction. The pressure inside is going to go down, and this simplifies to approximately 0.786 atmospheres. Okay, so that's the answer, but real quick, what does that mean? What does that mean? So if you don't know, atmospheric pressure of 1 atmosphere is approximately 14 pounds per square inch. Okay, so what that means is take something that's about a square inch. There's enough air pressure on that to exert 14 pounds of force on it. So if you've got a lid like this, I pulled a lid out of my pantry just to measure it, and I measured it to be about 12 square inches. So what that means is there is 12 times 14 pounds of air pressure on a lid like that, which is like it's about 175 pounds. Okay, so you probably know someone who weighs that much. Them standing on that jar lid, that's how much force the air is putting on it. Why doesn't the jar collapse? Well, because there's air inside also. So there's 175 pounds pressing down from the top, but there's also 175 pounds pushing up from underneath until it cools down. Now I've got 175 pounds pushing down, but only 78.6% of that pushing back up. Okay, so what that means is the equilibrium is off by almost a quarter. So that basically means that at the end, there's a net force in of about 40 pounds. So how difficult would it be to open this jar? It would be as difficult as lifting that lid if it had 40 pounds sitting on it. Anyway, between this and the last problem, that was a lot. So I'm not going to add anything else to that. I'll just I'll have something else for you tomorrow. All right. See ya.